So we're still working today on building the number theory background for the Shor's algorithm of quantum factoring. And again, the goal here is that I want to flesh out the mathematical structure that leads to the quantum advantage. And that's going to be the Fourier transform. So we want to see how the Fourier transform appears in this setting. Before I do that, before I move on, I just want to go back to, well, maybe I should go back to what we want to prove. If we have a composite number greater than 2, and we have x that's co-prime to n that has GCD equal to 1, then the probability of finding r, the order of x, to be even so that the square root of x to the r is not equal to -1 is going to be greater than or equal to 1 minus 1 over 2 to the n minus 1. And where x is chosen uniformly. But so this is the main claim that we want to prove, is that with high probability we can find an x where that will help us factor n. So again, this is going to be the main result that we want to prove for our algorithm to work. And then here in the previous lecture, we considered the base case where n was just equal to p to the alpha, where p is a prime and alpha is a positive integer. And the claim is that the probability that 2 to the d divides the order of x, where 2 to the d is the highest power of 2 that divides p minus 1, it's going to be equal to 1/2. We went through the arguments. We did a warm-up to show that if the period of x is equal to n, then m is another power that is equal to 1, then n divides m. And then we went through the proof, and we decompose the, we use this fact that the elements that have GCD equal to 1, which are the elements that have multiplicative inverse, you can generate them with one element as the powers of that element. And using that statement, we divided the elements that have multiplicative inverses that have GCD equal to 1 we divided it into two sets where k is even and k is odd. We showed that in the case k is odd, then 2 to the d divides r, the order, which is what we want to do. And we want to show that in the case k is even, it doesn't divide k is even, then 2 to the d doesn't divide r. So in here there was a small error in my logic. In here everything is okay up to this point. And in here we get to this point, so we start with 1 since the order of any element in Z mod n is going to be this phi, then any element to the phi is going to be equal to 1, and that means that when we rearrange these, g to the k is going to be to this power is going to be equal to 1, and that means that the order r of g to the k has to divide this number. So up to this point we're good, and we know that we have this number is equal to 2 to the d minus 1, and m is odd. And in here, what I actually wanted to say is that 2 to the d, this means that 2 to the d doesn't divide r. That's the correct statement that I wanted to make. And in particular, the reason is that if 2 to the d were to divide r, then by the transitivity property, that would mean that 2 to the d would divide this number. And this number is 2 to the d minus 1 times m, and m is odd. And that would have, and this has an extra power of 2. So this is 2 to the d, and this is 2 to the d minus 1. So that many 2's cannot go into phi over 2. So this is the contradiction that we wanted, and this shows that 2 to the d is not going to divide r. And so that's the statement that I wanted to prove. So there's a small error in the proof, and the correct statement is going to be this. The punchline is that we can partition the elements that have GCD equal to 1 into two sets that have the same cardinality. So that proofs are the statement that we want. Questions? All right, so now back to the beginning of lecture 13. So for this lecture 13, I actually want to, before we get to a Chinese remainder theorem, I want to prove this fact that I can generate all the elements that have GCD equal to 1 with one element by taking powers of this element. And before I move to a Chinese remainder theorem, which is, again, the Chinese remainder theorem is going to be our glue that takes us from the base case to any case. So this is going to put everything together. Now that we've established all the base cases, we can then use the Chinese remainder theorem to tackle any general case. And but before we move on to that, I want to prove that fact that we can generate the set of GCD equal to 1 by one element. And we need a technical lemma. This lemma comes from is it Donald Knuth?
Yeah.
All right, Donald Knuth. His book, The Art of Computer Programming, Volume 2, page 17. And it's actually, so I started reading the book just for this statement because the textbook that we have doesn't do the statement of the fact, it doesn't prove it. But reading the book, it was pretty interesting. He is doing a whole discussion about how to generate random numbers using modular arithmetic. So that's, if you ever wonder how computers generate random numbers, he has a whole discussion using modular arithmetic to generate random numbers. So, but he proves the statement that we need. And here, the statement is that, the technical statement is that if x is equal to 1 mod p to the alpha, and x is not equal to 1 mod p to the alpha plus 1, then x to the p is going to be equal to 1 mod p to the alpha plus 1, and x to the p is not going to be equal to 1 mod to the p alpha plus 2. So here, the subtleties is this alpha, the alpha power increases. So we have this, and then it implies if this is true, then you can just take p of both sides, and then you can add 1p in here and 1p in here. So this is the technical lemma that we're going to prove. Spoiler alert, it's going to be by the binomial theorem. The proof just follows the binomial theorem. So the initial hypothesis is that x is equal to 1 mod p to the alpha, and x is not equal to 1 mod p to the alpha 1 plus 1. So that means that we can write x is equal to 1 plus a multiple of p to the alpha, and m times m2 times a multiple of p to the alpha. So we can write it this way. So we get that from this. That's the definition of modular arithmetic. And additionally, by this fact, we get that the GCD of m, the multiple, and p is going to be equal to 1. If m had a multiple of p, then this would make x equals to 1 mod p to the alpha plus 1. Because you would have a p to the alpha and another p coming from here, and it would be p to the alpha plus 1. So we have that the multiple, the m times p to alpha, we have that m has GCD equal to 1. So now we just want to look at x to the p. And we take the representation that we have for x, 1 plus m times p to the alpha to the p, and we just do the binomial theorem. Binomial theorem, and this fact led to this representation, and this fact led to this GCD equal to 1. And we do the binomial theorem, And we see we have we want to prove two things, that x to the p is equal to 1 mod p to the alpha plus 1. And here you can see you have a power. You look at the coefficients and you have a power p to the alpha and you have an extra p coming from here. So this is going to have a power of p to the alpha plus 1. And then you have p to the 2 alpha, and this is a multiple of p. And so everything is going to have power of p to the alpha plus 1 or higher. So if you're just doing mod p to the alpha plus 1, all of these terms are going to go to 1. And so you obtain the first statement here, that x to the p is going to be equal to 1 mod p to the alpha plus 1. And then the second statement is that you want that x to the p is not equal to 1 mod p to the alpha plus 2. So you just look at the same expansion. In here, you have that the total power of this is m times p to the alpha plus 1. And m has GCD 1 with p, so there's not an additional power p in there. So when you do mod p alpha plus 2, then you still have this term. That's not equal to 0. But then the rest of the terms are going to have power p to the alpha plus 2 or higher. So the rest of these elements are going to be 0 mod p to the alpha plus 2. So everything goes to 0, but this element remains, and this means that x to the p is not equal to 1 mod p to the alpha plus 1 plus 2. Questions? Yeah.
Can you explain one more time why the later terms are mod 0 or 0 mod
p to the alpha 1. So in here, let's say alpha is equal to 3. And then in this case, this term would be, and so we're doing p mod, let's start with p mod alpha plus 1. So alpha plus 1 is equal to mod p to the 4. So in here, we would have p2 m2 p to the 2 times 3, 6. So this is equal to p multiple p2 m squared p squared times p to the 4. So it's a multiple of p to the 4. So that's equal to 0 mod p to the 4. And that happens for the rest of them because the power of p keeps increasing. And yeah, I think, yeah, it keeps increasing. There's a technical issue that I think p has to be greater than 2, and then p to the alpha has to be greater than 2 to make sure that it does increase or something like this. But this is the argument. Does that make sense?
I think so.
Yeah.
When you pulled out that p to the alpha plus 1 in the beginning, because it's not mod p to the alpha plus 2.
This one?
Uh-huh. All the other terms you said are mod p to the alpha plus 2 equal to 0.
Yeah.
If alpha equals 3, that third term wouldn't be 0.
So p to the alpha plus 2 is p to the 5. So p to the alpha plus 2 is equal to p to the 5, right? So and this third term, we can write it as so it's a multiple of p to the 5.
Okay.
Yeah, does that make sense?
Yeah, it's just a matter of writing.
Yeah. So I did p to the 4 just to be explicit that it is a multiple of p to the 4. So anything that has power of for alpha plus 1 or higher, then it's going to be 0. And then, if we're doing mod p to the alpha plus 1, if we're doing mod p alpha plus 2, anything that has a p to the power of alpha plus 2 or higher is equal to 0. It doesn't have to be a multiple of alpha plus 1 or alpha plus 2. It has to be just strictly higher.
Yeah.
Any other questions? So this is the technical lemma that we need. And now we're going to go to the proof that the set of elements with GCD equal to 1, and maybe I'll write it for clarity. This is x between x's between 0 and n minus 1, such that GCD of x, and I guess this is, in this case, p alpha minus 1, and p alpha is equal to 1. Then this set is generated by one element, G. And in here, I claim that it suffices to find x such that x to the p minus 1 is equal to 1 mod p, and x to the p minus 1 is not equal to 1 mod p squared. Which, it's essentially this hypothesis that we have for this statement. We have an element equals 1, and that same element is not equal to 1 mod p alpha versus mod p alpha plus 1. So in here, that element is going to be x to the p minus 1 and x to the p minus 1. One is equal to 1, the other one is not equal to 1. So it's the same hypothesis, this just that the element has a power of p minus 1. So by the lemma, if we take the p power of both sides, we have that it's going to be equal to mod, it's going to be equal to 1 mod p squared, and it's going to be not equal to 1 mod p cubed. And inductively, we can go up to p to the alpha, because again, this is going to be the hypothesis of our original lemma, and by the lemma, we can move to this statement, and then we can just apply the lemma again, because it's still the same hypothesis from the lemma, and we can just continue applying the lemma over and over again, until we get to the point alpha. And actually, the important thing that I want to get to is that I have this statement. This statement tells me that this x to the power p minus 1 times p to the alpha minus 1 is going to be equal to 1, which is what I want, is that it's going to be generating all the elements, and that before that, I didn't get to 1. So that I was taking, that means this statement is saying like I'm at an earlier power of x to the, at a smaller power of x, so somewhere along here in this generating sequence. And it says that that element is not going to be equal to 1. So somewhere along here, we're not going to be equal to 1. And then this statement says that if we then continue to the last one, this one's going to be equal to 1. And technically, if we're looking at the induction, I'm combining I'm essentially, actually let me, in the induction argument, or the final facts that I need is a combination of these two facts. They have to have the same power p to the alpha. And so I'm using part of the induction hypothesis and part of the result. But I want them to be, because I want them to have the same power of p. And the reason that I produced the third statement, this other result, is so that I can continue doing the hypothesis up to p to the alpha. But at the end, if I want the result for p to the alpha, I just need the result that these two statements. And then this is gonna show that we have the element x is gonna be equal to the generator. If, for instance, we know that the order of x has to divide this order, because of we know that the order of x are, by the statements that we did in previous class, the order of x has to divide the phi, which is going to be p minus 1 times p to the alpha minus 1. And so that means that r is going to be something like, say, p minus 1 times p beta. And if this was true, so and you assume that beta is less than alpha minus 1, if this was equal to 1, then you can do, so beta is going to be less than alpha, less than or equal to alpha minus 2, and then you have that alpha, then you can set m, is that good? Yeah, m is equal to alpha minus 2 minus beta, which is greater than or equal to 0. Then you have that you can write x to the p minus 1, p to the alpha minus 2 is equal to x to the p minus 1, p to the p2 beta times p to the m. So I can write it this way. And if x to the p minus 1 times p beta is equal to 1, then this would equal to 1, and this would be equal to 1 mod p alpha. And everything is mod p alpha. So if I had the order of x to be p minus 1 times p to the beta, where beta was less than or equal to alpha minus 2, then I can show that x to the p minus 1 times p alpha minus 2 is equal to 1 mod p to the alpha, which contradicts this statement, which contradicts this statement right here. So the fact that I have that this is not equal to 1, then, and this is equal to 1, then this really tells me that this is the order of x, and that this x indeed generates everything. Nothing else before, no other power of x can be equal to 1 before that. Otherwise, x to the p minus 1 to the p minus alpha 2 would be equal to 1. And here, I've reduced the problem to finding an x that does this, which means that you're going to show that we can do that. So p is a null prime given that x to the p minus 1 is equal to 1 mod p, and x to the p minus 1 is equal to, x to the p minus 1 is equal to 1 mod p squared, then I want you to show that if you add a p to it, then we're in the scenario that we want for the previous proof. So again, in here, to prove the statement, we just need to find an x that satisfies these two properties. So the idea is the following. Pick an x at random. If it satisfies these properties, that's your generator. If it doesn't satisfy those properties, then you're in this case. and then you add a p to that x, and then you found the element that satisfies your properties that will give you the generator. So in here, take a moment to show this, that if you have this, then you have this. And spoiler alert, what's going to be the strategy? Yeah, binomial expansion. All right, you're gonna walk me through it. So I have the binomial expansion of x plus p to the p minus 1. And I obtain this binomial expansion. And now I want to look at this modulo p squared. So for this term, modulo p squared, that's equal to what? 1. That's an easy one. And then let's go to the other easy ones. Everyone's clear why this is equal to 1? It's just by assumption. And then modulo p squared, what is this equal to?
0.
And what about the rest of the terms? 0. So now we have this last term here. And this is equal to p minus 1. This is equal to p. And is x to the p squared divisible by p?
If it were, then x to the p minus 1 would be equal to 1 mod p.
Yeah. So this is not going to have a p divisor. So in here we only have one p divisor. So it's not going to be equal to 0 mod p squared. So in here we have that p minus 1 xp squared xp minus 2p. We have that the GCD of p and p minus 1 xp minus 2 is not equal to, it's equal to 1. They have no common divisors. So that means that they have, that p squared doesn't have a common divisor with this, so this is going to be not equal to 0. So this is going to be not equal to 1 mod p squared. And so with that, we have that x plus p is going to be our generator. So if we just pick an element, and then if it happens that it doesn't satisfy the property we need for the hypothesis of the lemma, we just add p to it, and then we have the generator. Does that make sense? Yeah, if in particular, if x to the p minus 2 had a p divisor, then that means that x has a p divisor, which would mean that x is equal to 0 mod p. And that would mean that 0 to the p minus 1 is equal to 1. So that would be the contradiction. So we know that x doesn't have a p divisor. So p minus 1 times x to the p minus 2 times p only has one p divisor. So modulo p squared, it's going to be equal to not 0. All right. Any questions? Yeah.
Then fully, how do we know that x, how did this tell us that x was the generator? Okay.
X plus p is going to be the generator.
We said it suffices to find x such that it's only y suffices to.
Yeah, so it suffices to find x that satisfies this, right? And in here, assume you have an x that doesn't satisfy it.
Well, yeah, it's just why does it suffice? Why does it suffice to find x that does that?
This one. So we have this property, and then by repeated applications of the lemma, we have this. We have that x, maybe let me add a page. So in here we have that z mod p to the alpha z. The claim is that this is going to be equal to g squared all the way to g to the phi p alpha. And phi, we have that phi p alpha is, by definition, is just the number of elements here in this set. In this set here. Oh. And actually, we want to say the elements with GCD equal to 1. Did I have that here? Yeah. By definition, this is phi, so that means that, and we know for this case, this is equal to p minus 1, p alpha minus 1. So this is g to g p minus 1 and p alpha minus 1. So what I'm doing is I'm looking for an element, x, so that if I take or g, so that if I keep taking higher powers, they're all different numbers. And if I have, if there's a repetition somewhere in the middle, say I have g k1 is equal to g k2, then this is equivalent to g k2 minus k1 is equal to 1. So the period would be smaller than phi to the p alpha. So to ensure that I don't have any repetitions in this sequence of powers, then that means that the order has to be exactly phi of p to the alpha. And in this case, this is what, with this x, if we show this, then what I'm showing is that this x, the order of that element is equal to phi of p to the alpha. And we know the order of that element is equal to that because we know this property. If the order was smaller, if the order of x was less than p minus 1 times p to the alpha minus 1, then this would equal to 1. And the argument why it would be equal to 1 is by this reasoning, that if you have an order that's smaller, then you can rewrite this as the smaller order, and then multiply times p to the m, and it would be equal to 1. Does that make sense? Any other questions? All right. So we have, this is the last ingredient we need to prove the probabilistic statement that we wanted, that half the elements were divisible by 2 to the d. So now we're moving on to the Chinese remainder theorem. So this is, again, this is going to be the glue that's going to take us from the base case to a general case. And there's different versions or different ways to state the Chinese remainder theorem. Here's one particular high-level statement. It's saying that this set, if you take n to be any number and you look at its prime decomposition, then there is a bijection from C mod n to the tuples of C mod p to the alpha I. So in here, I have n, a prime decomposition with n different primes. And what I'm doing is I'm claiming that there's a bijection from the elements C mod n. So any element C mod n to a tuple, and actually this is m, to an m tuple of numbers mod p to the alpha I, pi to the alpha I. P1, pm. So again, we have x modulo n, and then an m tuple of other modulo pi to the alpha I. So there's a bijection between these two sets. And moreover, this bijection preserves the additive and multiplicative structure of both sides. And this is key. Because if I don't have that extra condition, additive and multiplicative structures combined, if I drop that condition, then the statement is trivial. Why is the statement trivial if I drop those conditions?
Prime decomposition.
Even smaller is even easier than that. So let me give you a hint. I have red, blue, magenta. And then I have another set, chair, desk, lamp. And I claim that there's a bijection between these two sets. Is there a bijection? Yeah, you can just map something to something, whatever color to something. The two sets are the same size. So you can create a map from one to the other. But in here, the content of this is that we actually preserve the multiplicative structure and the additive structure. In here, these two sets on the left and the right have the same cardinality and they're finite sets. So there will be a bijection. And there's many bijections. But the important part here is that we're preserving the multiplicative structure and the additive structure. So let's check it out. And here, the easiest non-trivial case is n equals 6, 2 times 3. The Chinese remainder theorem claims that there is a bijection between the integers mod 6 times the tuple of integers mod 2 and integers mod 3. And in particular, this is the way the bijection works specifically. For x mod 6, you map it to the tuple of x mod 2 and x mod 3. And for a tuple of y1 mod 2, and this is going to be y2 mod 3, if you take this tuple, then you map it to 3y1 plus 4y2 mod 6. And that's going to give you the bijection. That's going to be the map going forward, and that's going to be a map going backwards. So for instance, you can take 0, mod 2 mod 3, it's going to be 0, 0. 1 mod 2 mod 3, it's going to be 1, 1. 2 mod 2 mod 3 is going to be 0, 2. 3 mod 2 mod 3 is going to be 1, 0. 4 mod 2 mod 3, 0, 1. And 5 mod 2 mod 3, 1, 2. And here, I'm checking that the additive structure is preserved. And in this case, we can do it by hand. It's just doing an addition table. And in here, we're familiar with the additive structure of mod 6. In this right-hand side, the additive structure is component-wise. So in here, 0, 0, I just add this element. It's actually the additive structure. If I have a tuple, A1, A2 plus B1, B2, it's just going to be equal to A1 plus B1 and A2 plus B2. This is the additive structure component-wise. So the idea is that the additive structure matches. So let's continue filling out the addition table. What's this number here? 0. What's this number here? 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 And now let's go to this number here. 0, 0. What's this number here? Are you guys checking it or just going with the pattern?
I'm still copying down the other numbers.
You're still copying down the other numbers. So let's actually check this instead of going with the pattern so far. So this one is 0, 1, and 1, 0, so 1, 1. And then let's check another one here. This is 0, 1 plus 0, 1. It's going to be 0, 2. And this one, it's going to be 1, 2 plus 1, 0, 0, 2. And this is going to be 0, 2. And then here, 1, 2 plus 0, 1 is going to be 1, 0, 1, 0. And then the last one is going to be 0, 0, 1. Now, is this the same additive structure? And ideally, what you would have to check is that all the numbers given this bijection, you gotta check that this number and this number are the same for each place in the table. But you should probably convince yourself that it's true based on the diagonal structure. That's a good hint that everything's happening the same. You can see that along this, there's this pattern of the diagonals being constant. And you can see the same pattern in the diagonals. So that's a small hint that this is going to be the same additive structure. But technically, you should check everything. But here you can already start seeing that the same additive structure. Yes?
Where did the 3y1 plus 4y2 come from?
Ooh, that's a good question. And that's the proof of the Chinese remainder theorem. They give you a recipe to actually map back. And we'll give you so in here I pulled it out of nowhere. And, when I prove the Chinese remainder theorem, I'm gonna give you the recipe for 3 and 4. And then we can check that it's going to be a bijection. So that's a good question. And we can even check it. So for instance, this 1, 1, if we do the recipe, it's going to map to 3 plus 4, mod 6, that's going to be equal to 1. So it's non-trivial to find this numbers 3 and 4. It's a little bit tricky, but with a clever choice, you can see that it's going to map you to the right thing. 0, 2, if you do, you put it here, it's going to be 8, mod 6 is going to be equal to 2. So you can go through it and check that it gives you the bijection. So in the next class, we'll start with this. We're going to do the multiplicative structure and check that it's the same. And then the other thing to do is prove that this is the best statement that we can do. In particular, we're going to show that this case doesn't actually work. So in here we are doing 6 and we can factor it into 2 and 3. But if we have the same prime power, we cannot factor it into each of its components. We can just leave it, the smallest we can do is p 2 squared. We can't go any further. And here we'll check that the additive structure doesn't match to see that more of the details of the Chinese remainder theorem. And that's class.